Hi there, folks. Today we're talking about similar figures, all right? Similar figures are basically objects of the same shape, but not necessarily the same size, okay? And so if you kind of think about like something like an action figure, all right? An action figure is supposed to look like, the real version of that thing, but it's smaller, it's scaled down, all right? If you've ever had like a toy as a kid that was supposed to mimic something else, like my son has a toy tractor, okay, that he can ride around on. It's not the same size as a regular tractor, but it's meant to replicate the shape, and it has the same details and that kind of thing. So it's the same shape, but a different size, okay? And so we use this little tilde symbol to mean similar. And so if we look at these two objects, we can see they're the same shape, all right, but they're not the same size. One is a smaller version of the other, or maybe one is a bigger version of the other, all right? And so we say they're similar, and we name them by the corresponding vertices, just like we do when we're talking about congruent figures. We got to make sure the pieces match. Well, in this case, the pieces don't match in terms of congruence necessarily. For the angles, they do. They match in terms of congruence, but the sides, they match in terms of factor, in terms of the scaling, that kind of thing. All right, so we kind of match up these common vertices. So if I called the first one A, B, C, D, I would say that's similar to, I would have to call the second one, sorry, that's a terrible looking tilde symbol. The second one would be W, X, Y, Z. I have to go in the same order for the second one as I did for the first one. And, those angles have a special relationship. They match up. And the sides have a special relationship as well, okay? And so let's talk about those relationships. So similar, same shape, different size. If the polygons are similar, the relationship between the angles is the angles are still congruent, all right? So the angles are still congruent because the angle measurements give us ratios for the sides in terms of that. Like, think back to something like triangles. If you looked at an equilateral triangle, all the angles are 60 degrees. If I look at another equilateral triangle, all the angles are 60 degrees. If I look at another equilateral triangle, all the angles are 60 degrees. And so there's a relationship in terms of the size of the angle and size of the side within one triangle, but not necessarily when we compare two different triangles, okay? And so as we look at this thing, the angle measurements stay the same as we go from one size triangle to the next, and that's true for all similar figures, okay? The angles, the corresponding angles are congruent, but then the side lengths are proportional, okay? We can see, like, again, in the example I gave up here, this thing getting bigger. Maybe this is 1 unit. Maybe this is 2 units. Maybe this is 3 units, okay? And so those sides would correspond. Let's say this was a 4. Well, then this one would have to be an 8. There's proportionality there. To get from the first triangle to the second triangle, I multiplied that one side by 2. Well, that means I multiply all the sides by 2 to get the respective sides. Okay, and that kind of thing. Over here, this one would be a 12, okay? Because looking at the first one, it's 1 times 3 gives me that one side. It has to be 4 times 3 to give me the other side, okay? That idea of proportionality, all right? The angles are congruent, the sides are proportional. And so if I look at this guy, I have two similar figures here. If we want to talk about the angles, well, I can easily say that by matching these up in terms of the position, in terms of the naming, that angle A would be congruent to angle W. I could say that angle B is going to be congruent to angle X. Angle C is going to be congruent to angle Y. And angle D is going to be congruent to angle Z. And, all that makes sense if you really think about, what we've done in terms of polygons and angles, all right? All quadrilaterals have the same sum for angles. All squares have all right angles, regardless of the size of the square. All rectangles have right angles for those, regardless of the size. The angle measurements are congruent, okay? The scale factor is the special name we give to the ratio that corresponding the linear measurements of the two similar figures. So to get from one figure to the other figure, the scale factor is essentially what we multiply by. It's the ratio that gets me from one side length to the other side, to the corresponding side length, okay? And so if I look at something like this guy, if I were to kind of compare these two and say, hey, to get from the big triangle to the little triangle, I have to think about the scale factor. Well, big to little or little to big, if I compare these, like if I compare the corresponding sides, this one and this one, if I were to compare those, let's say I compared it this way and said, hey, 8 over 20. So 8 over 20, that reduces to a 2 over 5. So 2 over 5 becomes the scale factor to get from the big triangle to the little triangle. If I were to multiply this 20 by a 2 over 5, it gives me an 8. If I were to multiply this 25 by a 2 over 5, it gives me a 10. If I were to multiply this 15 by 2 over 5, it gives me the 6. And that's why we call it a scale factor. It basically becomes the thing we multiply to get from one to the other. If I wanted to go backwards, if I want to get from the little triangle to the big triangle, the scale factor to get from one to the other would have to be 5 over 2. And so that's what I would multiply by, all right? And so when we think about scale factors, again, it's the way that we scale down from one to the other or scale up from one to the other, okay? It's the thing we multiply by to get that side length. And it doesn't matter which side we had chosen. Had I chosen the 25 and the 10, if I do it in the same order, that also reduces to a 2 over 5. Had I chosen the 15 and the 6 over 15, that also reduces to a 2 over 5. And that's the other idea behind similarity here. We don't just want to find the scale factor. Yeah, the scale factor is important. It gets us from one to the other. But in order for two things to be similar, the scale factor has to be the same no matter which sides we compare. Every side has to give me the same ratio when I compare those corresponding sides. If one of them gives me a 2 over 5 and another one gives me a 1 over 4, then these are not similar figures, okay? And so that's the idea here. All the angles have to be congruent. All the sides have to be proportional, okay? So no matter which pair of sides I compare, if I compare the corresponding sides, it should give me the same ratio every time, okay? And that ratio then becomes a scale factor. It becomes a way to get from one version of this thing to the other, okay? If I look at something like this guy, it says, name any similar figures and justify your answer. So if I look at this thing, again, the two criteria I need are that the angles are congruent and that all the corresponding sides give me the same ratio, that I have a scale factor, that they're proportional, okay? And so as I look at this thing, I look at A and I look at W, and I see the same number of arcs, so those angles are congruent. I look at B and X, and those angles are congruent. I look at C and Y, and those angles are congruent. I look at D and Z, and those angles are congruent. So right away, as I look at this thing, I have all the congruent angles that I need, okay? So all corresponding angles are congruent. Let's make a note of that. Okay, so that's step one. All corresponding angles are congruent. I just have to compare the sides and see if I get the same ratio, the same scale factor each time. And this one's a pretty easy one as you look at like something like 12. To get from 12 to 6, well, that's times 1/2. So I could say the ratio is 6 over 12 or 1/2. So the ratio of AB and WX, or WX to AB, is 1/2. If I were to compare the next sides, the 24 and the 16, if I think about the scale factor there, 16 over 24, the ratio of the small one to the big one, well, that's going to be a 2/3. If I look at the ratio of this guy to this guy, again, that's a 7 over 12. And then if I look at the ratio of this guy to this guy, they're both 6s. That's a 1-to-1 ratio, so the ratio is 1 over 1, which is 1, 6 over 6. And so as I look at this, as I compare corresponding sides, I get a different ratio each time. And that's no good. If I get a different ratio each time, then these are not similar figures. The sides are not proportional because I don't get the same ratio each time, okay? So no, these ones are not similar figures. And it's because the sides are not proportional. Okay, I got a different ratio each time. Okay? If I look at the next one, same kind of thing. I start with the angles. I say, okay. If I look at G and M, same number of arcs, so those are congruent. O and I are congruent, and J and T are congruent. So as I match up all of these angles, each of the corresponding angles is congruent to its corresponding angle in the other triangle. So the angles work, so all the corresponding angles are congruent. So now I have to compare the sides. And again, I just work my way around and say, okay, 15 and 12, that one's a little bit harder to identify than the previous one, so it's 12 over 15, which reduces to, a 4 over 5. 12 over 15 reduces to 4 over 5. So then I compare the next set. Again, I have to look at corresponding sides. These two sides correspond, the 16 and the 20. So if I wrote those as a ratio, 16 over 20 reduces to a 4 over 5. So looking good so far. I've got two that are the same. I have to compare the third one, though. Here we go. If I compare these guys, 8 over 10, that reduces to a 4 over 5. And so you notice here, I got the same ratio each time when I compared the corresponding sides. So that means the sides are all proportional. Okay? The ratio to get from one side to its corresponding side is the same as any other side to its corresponding side. Okay? So I could say, yes, these are similar. And they're similar because corresponding angles are congruent, and the corresponding sides are proportional. Okay, that's it. Not happy with that symbol. And since these are similar, let me write a similarity statement. So I'm going to call the first one triangle GIJ. And I'll say that's similar to, I got to make sure that I label this properly. So it's going to be MOT. Okay? If I look at something like this guy, it says that ABCD is similar to EFGD, and I want to find X and Y, okay? And so I have two trapezoids here, one big trapezoid and then a smaller trapezoid inside, and since the two are similar, I know quite a bit about their angles, but if I look at this, this is talking about their sides, okay? I know that all the angles are congruent, but this is talking about their sides. And so if the sides all give me the same ratio, as I compare those sides, like if I compared the X, that side, I missed the F here. There we go, F. So side FG, I would compare to side BC. That would be the ratio X over 7.5. Okay? If I compared the side that had Y, the EF, okay, that would be EF, which is Y, would compare to the bigger one, which is 5. And notice that I'm keeping each of these ratios in the same order. The first one was little over big. The next one is little over big. And if we look at that proportion that I've written, since each of those ratios has to be the same, they're equal, I have a proportion, I can't solve that proportion, right? That one doesn't work because I have too many variables, so I have to keep going. And this is the key right here. It's this side right here. This is the tricky one, okay? The ratio that I get here, if the smaller trapezoid is a 6, the larger trapezoid, students get fooled here and they write down a 3, but the larger trapezoid, think about the sides. The smaller trapezoid was side ED. The larger trapezoid is side AD, which is actually 9 units, okay? Now I have a ratio that I can use to solve these. And notice I've kind of written this almost like an extended ratio, like an extended proportion. If I want to solve this, it means any one of these ratios can be equal. So I could do something like this. I could say, you know what? Let me just ignore the Y for a second. Let me just do these ratios are equal, okay? And separately, I could have done the Y first. It doesn't really matter. But now from here, I want to solve this thing. So I'm going to cross multiply. So 6 times the 7.5 gives me a 45. And x times the 9, so that's a 9x equals 45. I divide each side, and I get x equals a 5. Okay? So there's x. I can do the same thing with y. And, I could use this ratio now. I could rewrite this one as 5 over 7.5. I'll always go back to that original ratio of 6 over 9, the one that had all the numbers that I knew, just in case I have like a decimal approximation for x. I don't want to reuse that ratio. So use the one that you know for sure. and that's going to equal y over 5. Okay? We need one of these ratios to have all numbers in it if I want to solve for a variable. Okay? Or at the very least have the same variable. So here I get 9y equals 30, and then I have to divide each side by the 9. Okay? And see, if I had done this one first, this one gives me like a 3.3 repeating. Okay? If I had done that one first, that would not be a good ratio to use. 3.3 over 5, that wouldn't be a good ratio to use to find x because I have a rounded off value. And that's why I always go back to this one that I know for sure, that was given based on the picture. Okay? So again, similar figures, all the corresponding angles are congruent. All the corresponding sides are proportional, meaning if I compare corresponding sides, I should get the same ratio every time. All right? And that allows me to solve because I can set up these as proportions and I can cross multiply and I can solve. All right?